Hello, everyone. Today, I'll be presenting my work on dependent test-aware regression testing techniques. My name is Wing. This work was done in collaboration with August and Reed from the University of Illinois, along with Sai from Google, Mike from University of Washington, and Tao from Peking University. So let's first take a look at what a flaky test is. A flaky test is essentially a test that passes and fails when you run it in the same test scenario. In this case, being the same version of code, the same configuration to run the tests, and so forth. One prominent type of flaky tests are order-dependent tests. Essentially, these are tests that are flaky only due to the order in which you run the tests. An example of an order-dependent test is shown here. This test is from an Apache project with over 6,000 stars on GitHub. Specifically, what these two tests are doing is that the first test with line 3, it's checking whether or not an instance of a class variable is already shut down. But the instance can actually be started and not shut down by some other tests, like the one at line 7. And so what happens when you run these two tests is that if you see the T1 and then T2 run, then both tests will pass. But if you, by chance, see T2 and then T1 run, then T1 will actually fail. So why is this a problem? Why do we care about these tests? Well, for one, it actually makes test outcomes inconsistent. And because of that, they may lead developers to manually debug some non-existent faults in their recent changes and waste their time and machine resources to rerun tests. They also affect regression testing algorithms. So again, with a simple example here of 3 tests, T1, T2, and T3 run in that order, we would see all 3 tests pass. With test prioritization, we may see T2, T1, and T3 as the order, and in this case, T1 fails, like the example we looked at before. In test selection, we may select only T3, and now T3 fails. And we may do test parallelization, where T3 gets put on its own machine, and again, we see T3 fail. In fact, from our previous work, we've actually even found that many existing work kind of assumes that there are no order-dependent tests, especially in work like test prioritization, test selection, test parallelization, and even test generation. Specifically, in papers from ISSTA and so forth, we see that about 87% of them assumes that there are no order-dependent tests without any justification. We also found that as a threat to validity, that 10% of them claim it in there, and that's it. And finally, there was about 3% that actually considered order-dependent tests. So now that we see that order-dependent tests can, in theory, affect these regression testing algorithms, the question is how much? So in order to help with this, we first help understand the impact of these order-dependent tests on these regression testing algorithms. And then we want to look into how one can actually make these algorithms dependent test aware. To help with this, we first perform a study on order-dependent tests and how they affect regression testing algorithms. We then present an approach to help enhance traditional regression testing algorithms so that they become dependent test aware. And finally, we perform an evaluation on 12 of the enhanced regression testing algorithms to see how they compare to the unenhanced ones. For our study, we first selected subjects from our previous work, which created a data set of flaky tests with GitHub projects from specifically 8 real-world ones. These 8 real-world projects in total contains about 3,300 human-written tests. With the popularity of automatically generated test suites, we also use Randoop, a state-of-the-art automatic test generation tool, to create over 18,000 automatically generated tests. From these human-written ones, we find that 111 of them are actually order-dependent. From the automatically generated tests, we find that about 28 of them are order-dependent. Although the number of order-dependent tests here might be kind of small relative to the entire test suite, it's important to understand that their impact can still be substantial, as we will show in the next few slides. So now let's look at one of the testing algorithms specifically, test prioritization. In test prioritization's case, we have a test execution order, and what test prioritization will do is it will give us a new test execution order. This order will help us achieve coverage faster and improve the fault detection rate. But one thing to note here is that the developer expects, no matter if they run it in the first, on the test execution order on the left-hand side or the right-hand side, they expect that each test should yield the same result. For test prioritization, we looked at 4 main algorithms, essentially ones that prioritize based on statements or methods, and ones that prioritize based on statements that haven't been covered, or statements just in the absolute number relative to the test. So overall, we find that there's about a 23% of the order-dependent tests that are human-written was actually manifest when we use test prioritization algorithms. One interesting thing to note here is that the not yet covered algorithms do tend to have more order-dependent tests than the other ones. Specifically, when we manually investigated some of these, we find that many of these order-dependent tests fail if one particular test is run before them. And in the not yet covered orders, generally that dependent test somehow happens to be in between the order-dependent tests, again, based on its coverage. Versus in the other orders, the dependent test was always running after the order-dependent test, and consequently, all the other ones, the other algorithms tend to have much lower number of tests that was found. Overall, we find that there's a modest chance for these order-dependent tests to affect these test prioritization algorithms, especially with these human-written tests. In terms of automatically generated tests, we do see that the change becomes quite a bit more drastic. In fact, we do see that it goes up to about 54% of the automatically generated tests that are order-dependent seems to have actually been revealed when we actually use test prioritization algorithms. Now let's switch to look at test selection instead. In test selection's case, you have a test execution order, and what test selection does is it gives you a subset of the test execution order to run. The idea here is that you can run them faster and get your results faster. Again, though, the developer's expectation here would be that no matter if I executed the entire test execution order or just a subset of it, each test should yield the same result. For test selection, we looked at 6 different algorithms. Ones that essentially consider statements versus methods, and ones that do some reordering versus ones that do no reordering. The ones that do reordering is essentially a combination of first doing test selection followed by test prioritization. In the case of test selection, we do see that it comes out to be about 24% of the order-dependent tests for human-written ones did get found when we actually used a test selection algorithm. One thing to note here is that these ordering algorithms do tend to actually have more order-dependent tests than the ones that do no reordering. So if you do happen to use test selection followed by test prioritization, it is especially important that you have a solution to help deal with these order-dependent tests. Overall, we find that there's a modest chance for order-dependent tests to affect these test selection algorithms, specifically for human-written tests. On the other hand, for automatically generated tests, we see that the test selection algorithms actually are rarely actually affected by order-dependent tests. In fact, we only saw one test that happened to have been selected for the different versions that we use for our subjects and was order-dependent for the automatically generated ones. Lastly, let's switch and take a look at test parallelization. In the case of test parallelization, you have a test execution order that all of its tests are essentially split across different machines and run on those different machines. The idea here is actually to reduce the test latency, the time it actually takes in order to get the final result for all the tests. Again, the developer's expectation here would be whether if I ran these tests on different machines or if I ran them on one machine in this one test execution order, they should all yield the same result. For test parallelization, we looked at 2 different algorithms. If you parallelize by test ID, which essentially is just parallelizing based on which machine has the least amount of tests, or if you parallelize by test execution time. So based on the last time you executed these tests, how long it took, you use that information to parallelize. Overall, we see that there is a low chance actually for these order-dependent tests to affect test parallelization. In fact, we only saw about 6 of them out of the 111. In terms of automatically generated tests, we see that number do go up quite a bit. Again, it's also because the results for parallelizing based on test execution time do seem to see quite a bit more order-dependent tests found because of the reordering that it can potentially do. Overall, we see that the impact of these order-dependent tests ranges quite a bit, but there are a number of them that do have modest to high impact chances. And the other thing that I would caution you on is that these order-dependent tests did affect all of the regression testing algorithms that we looked at least one of the modules that we studied. So now that we see that order-dependent tests can affect these regression testing algorithms quite a bit, one natural question is how can we actually enhance these traditional regression testing algorithms so that they can be dependent test aware and be less affected by these order-dependent tests? Essentially, before we jump into that though, I will say though that order-dependent tests do provide developers some benefit. Specifically, it helps developers run their tests faster. In fact, when we actually looked on these open source software on GitHub, searching for annotations and attributes that helps developers run tests in specific orderings, we find them to be used in almost 200K files on these open source software. We also see that there has been various tools in recent years to help developers automatically find these test dependencies. And so one natural question here is, how can we actually enhance these traditional regression testing algorithms with some of these known test dependencies from developers or tools so that they become dependent test aware? So to help with this issue, we propose a general approach to help enhance these regression testing algorithms. Our approach is largely in two main steps. The first one is we generate the unenhanced regression testing order. We then reorder and add tests to the existing order so that we can output an order that would respect all of the provided dependencies. The input to our approach is simply the metadata that you would have used for the unenhanced regression testing algorithms, the original order in which the tests would have run by default, and a set of test dependencies. And finally, with all this information, we would output an enhanced regression testing order that respects all of the input test dependencies. So here is, we can go over each step of the approach. As input, again, we take the metadata, the original order, and a set of test dependencies. Our first step is to use the metadata and the original order on the unenhanced regression testing algorithm to get an unenhanced order. Using that order and the test dependencies, we then provide that to the enhanced regression testing algorithm that would actually then use that information to finally output an enhanced regression testing order that respects all of the input test dependencies. So now that we've shared with you our approach, we want to share with you how this approach would actually perform when we looked at 12 different enhanced regression testing algorithms on the subjects that we talked about earlier in our study. Specifically, for our experimental setup, we largely care about two main metrics. The first metric is how effective our enhanced approach really is at actually reducing order-dependent test failure. The second one is on the efficiency. So when we actually, in terms of test selection, test parallelization, we may actually have to add tests to those to the test selection orders and to the test parallelization orders. And because of that, it can actually make those orders slower. So we want to look at, for the time that these unenhanced orders would have taken to run, how does that compare to the enhanced ones? All of the versions that we select for our subjects must pass in an original order, and they must have some code changes in them. And for each of the subjects that we talked about earlier, we actually select up to about 10 different project versions for them. So what we do is that on the first version, we would actually compute all of the input. So this includes the metadata, the original order, and the test dependencies. The way we get the test dependencies is we use automated tools. For more details on how we use the automated tools and which ones we used, please see the paper for those details. Once we've computed the input, we then take those inputs and use them on the second version and the subsequent versions of this subject. Specifically for test prioritization and test parallelization, we use them on the second version, and we see how the metadata, original order, and test dependencies would perform with and without our approach for the regression testing orders. We then also use it for selection as well, where we would use it on all subsequent versions. So we would use it on the second version as well, along with all the subsequent versions, using the same metadata calculated on the first version. The reason we do it this way is that by doing this, we also want to show that if you calculate the metadata, original order, and test dependencies infrequently, they can still be useful for many versions down the line. Overall, in terms of the effectiveness of reducing order-dependent test failures, we see that for 16 actually of the 26 enhanced orders that we looked at here, that turns out to be about 62% of them, we can actually completely eliminate all order-dependent test failures. We also see that when you start combining these different types of tests and the modules together, the enhanced algorithms overall can reduce the number of order-dependent test failures by about 80%. In terms of the efficiency of these orders, again, because our enhanced approach can add tests to test selection and test parallelization orders, we can actually be slower sometimes. And we can see that by the positive numbers on this table. But what we also see, though, is that there are some cases where we actually have negative numbers. And this is very interesting because what this is saying is that because we added tests, we are actually running faster. And the reason for this is because when we investigated these cases, we find that the order-dependent test failures from the unenhanced algorithms actually would cause the order-dependent test to fail. And because of that, it actually slows down the runtime of the test because these order-dependent tests are waiting for some resource, perhaps. Overall, we find that the runtime slowdown of these unenhanced orders compared to the unenhanced ones is only about 1% slower across all types of tests for all of the modules. So in conclusion, we find that most of the existing regression testing work don't really account for test dependencies. And yet developers are writing them, and they can be obtained automatically with tools. Because of this, we want to understand the impact of these order-dependent tests on these regression testing algorithms and how one can actually make them dependent test aware to alleviate the impact of these order-dependent tests. We accomplished this by first performing a study to understand how order-dependent tests affect these algorithms. We then propose an approach to make regression testing algorithms dependent test aware. And finally, we show an evaluation of how our approach performs, showing that you can actually have substantially fewer order-dependent test failures while only being marginally slower. Thanks. I'll take any questions at this point.